Good. Let's jump over to Lisa's talk, I would say. And so after the talk, there will be time for questions. Also, I will monitor the chat for online friends' questions, so feel free to drop them in whenever. Okay. Thank you, Alma. So yeah, welcome to this presentation. I'll be presenting some work that some colleagues at Momentum and I worked on in the last few months, and actually out of it came a paper which is going to be presented next week in a workshop at Neurix. So yeah, we're very excited about this as well. So the paper is on multiscale neural operators for solving PDEs. And today I'll take you to a little bit of I'll take you through some context on why PDEs are relevant around us, and looking at how they can be solved specifically using graph neural networks. And then I'll introduce you to our rewiring strategy that we introduced in the paper. And also we'll look at how this can be applied to some data sets, real-world data sets, and the results that we have. So first, let's define a little bit what PDEs are. So PDEs describe a range of physical phenomena around us. It can describe the weather, the magnetic field of a motor, fluids, simulations, and a range of other applications. And yes, so we are looking at solving these PDEs. They describe as a physical quantity that's moving in space and time. And these can be solved more traditionally with running simulations by an engineer just running a physical simulation over and over for different parameters. But they can also be solved with deep learning. And the advantage of using these neural operators is that we can get much faster iterations and can just feed the model with a bunch of data, and the model can then work on different parameters of the PDE. So an example of this is like a work that was done a couple of years ago, which was kind of revolutionary on finding predictions for the Navier-Stokes equation. It's an equation in fluid dynamics, and it had really accurate results, as you can see from the animation. And actually, this was quite popular, so much so that it was tweeted by the rapper MC Hammer, so it's very relevant. And it's also used in like weather forecasting. So you might have heard of GraphCast that DeepMind came out with recently, and they actually use graph neural networks to predict the weather very accurately using this model. So yeah, you can kind of see how relevant it is to the world around us. And more specifically, related to our projects at Momentum, we work with an automotive manufacturer, which is looking to predict the electric field of the magnetic field, sorry, of an electric motor from the layout of its components. So our input is the topology, and our output would be the magnetic field, and that's described by a PDE, and we can solve it using GNS.
Could you quickly juxtapose time-dependent or time-independent?
Yes, yeah, of course. So yeah, time in this setting we're looking specifically at time-dependent, which just time-independent, which just means that you go from the starting state to an end state directly, and it doesn't evolve in time. That's just like you have one dimension less to consider essentially, so you're just considering spatial dimensions and not the time dimension. So yeah, looking at a specific problem of the motor, we can get from our input data a mesh of the PDE. And when we look at this mesh, you can see that there's areas that have very high load density and areas where it's less dense. And when we look at solving these PDEs, we can consider, like in the literature, they've considered using, for example, convolutional neural networks. And that means discretizing the input into like structured grids of image, so with pixels. And you can see that like in this area of high node density, so here, it doesn't really resolve as well as we'd like to. And if instead we use the original mesh and process this, we're able to really recover the granularity that you would want in these very dense areas. And that's kind of the motivation behind using graph neural networks, because they're particularly well suited to processing these meshes. So let's go through a little bit of background on graph neural networks. Graph neural networks process graphs, surprisingly. And the graph just represents attributes of the data as nodes, so these are nodes, and then they're related to each other through edges. And so graph neural networks, they learn, they optimize a transformation of the graph. And how they do this is through the message passing operation. So message passing aggregates the attributes of neighboring nodes and then transforms it and then updates the graph. So for example, if we take this node and we, in message passing, we would take that embedding and the embedding of the nodes that are related to it. So these two nodes have edges to it. And we will aggregate this. You can use different ways of doing this, like there's many different flavors of GNS. And then you pass it through this learnable transformation and updates with the new graph information. And that's how we're able to propagate information throughout the graph when we do this for every node in the graph. But you can see like this really works with the like message passing is dealing with the nearest neighbors. And so if you have a very large graph, you want to propagate the information all around the graph. And that requires essentially stacking different layers of message passing on top of each other. And that's what graph neural networks do. So like in the zeroth layer here, if you consider this as our reference node, this yellow node, in the zeroth layer, you deal with like the first nearest neighbors, then you get information from the second, etc., etc. And if we want to get information across very large distances, so like these two nodes, which are like third or fourth nearest neighbors of that node, then we have the option to either stack a lot of message passing layers on top of each other, or we can consider methods that would kind of create highways between these nodes. So they will create edges that directly relate the two nodes. And that's kind of what we're considering in this work, because as you saw from the picture of the motor, we sometimes have to deal with like very dense areas where you want to deal with very local interactions, but you also want to propagate the information across to the whole graph. And for that very dense graphs, that can be complicated if you just have to stack many message passing layers on top of each other. So we looked in this paper at applying different methods in the literature to our specific problem with the motor. And one of these is using hierarchical GNNs. So if you're familiar with convolutional units, this might look kind of familiar to you. And the hierarchical GNNs work in a similar way. So they have an encoding and decoding process where you start with a dense graph, and then you downsample it. So you select a selection of nodes at each kind of level as you go downwards, and you end up with a very coarse graph, and then you go back to the very dense graph. And the idea is that when you are at the top of the U, you're able to handle these very local interactions, and then when you go to the bottom of the U, you're able to have these more long-range interactions between the nodes. So we're able to pass messages at various levels in the graph and have a more of a propagation of information across the mesh. Another way that's been investigated in the literature is using graph rewiring. So that just means supplementing the original graph with additional edges. And like one way that you could do this as a form of global rewiring is just the attention mechanism. So I assume you'd be familiar with the attention mechanism used in transformers and NLP. And this just means that you're connecting every single node in the graph. In the graph context, at least, it means you're connecting every single node to every other node. So you're creating a fully connected graph. And so we investigated two existing state-of-the-art methods. One on hierarchical GNNs called BSMS. So it selects the nodes as you go through the U in a very particular way. I won't go into too much detail, but that was one method that we applied to our data sets. And we also applied transformer receiver IO as a graph rewiring method. So we had these two methods as kind of baselines to test against. And we also thought of another graph of our own rewiring method. That's kind of in between the two, so it involves rewiring, but also this hierarchy, like creating different levels in the graph. And the aim of this was to select kind of intelligently the nodes that you're going to have these long-range relationships between, or at least in a little bit of a clever way rather than just randomly selecting nodes at each level, for example. So our method works in two main steps. The first one is that we're creating a binary tree from the graph. And the second one is then we're adding these hierarchical edges. So we begin by creating a binary tree. So if we have our graph here, we just split along the spatial dimension that has highest variance, and we do this recursively over multiple levels. You can set the number of levels as a hyperparameter. And then you end up with different bins. So here, in this case, we have 4 different bins that are color-coded. And from this, you start adding the hierarchical edges in your graph. So at the very basic level, you supplement your graph with edges that relate the center node of each bin to every other node in the bin. And the center node is just defined as the node that's closest to the mean position of nodes in that bin. So this is the center node of the blue bin, etc., etc. And you relate every other node in that bin to it. And then you start merging the bins until no bins are left. And that creates these longer range edges between nodes in your graphs and just allows us to supplement these like highways that I was talking about earlier. And so we do this by merging 2 bins, and then we do this until all the bins are merged. And in our method, we also provide an extra hyperparameter that you can set. So you can set how granular you want your levels to be by controlling how many levels you merge at once. So yeah, these animations show if you, from what I was showing earlier, if you just merge each level, you merge 2 bins, it gives you these 4 different levels. But if you merge 4 bins at each level, then you only get 2 different levels. And again, that's like a hyperparameter that you can set in your implementation. So yeah, I've talked about different ways of passing messages across different scales in our mesh. And also, like one way, our kind of baseline that we're evaluating against is this just message passing directly on the mesh. And from this message passing, our method allows us to simply be applied in a pre-processing step. You just supplement the graph with these additional edges, and then you can apply any message passing operation that you want. So we have these tree edges. We end up with these tree edges that are supplemented, and then we compare it to the SMS, so the hierarchical GNNs, and Perceiver, the transformer graph rewiring. So before I show you some results from our methods, I'm just going to go through some data sets that we tested on, because we wanted our method, even though the motor data set was kind of our main focus and showing the main challenges that we were looking to deal with, we also wanted to test this with different challenges. So the Darcy flow data set, its particularity is that it has a regular grid, and it's predicting the flow through a porous medium from the viscosity of the fluid. And through this, because we have this regular grid, we can actually apply the convolutional neural networks that I was talking about. And it allowed us to validate our methods and see how our graph neural network-based methods compared against the convolutional neural networks. Then we have the motor data set, which I've already introduced. So here we have this irregular grid. We can no longer apply the convolutional units. And we also have a much higher node density. So in the Darcy flow, we had around 16,000 nodes per sample, but here we're dealing with around 30,000. And also to test for generalization, so something that's pretty important in deep learning, we had this magnetostatics simulations data set, and its particularity is that it deals with also irregular meshes, but its training set has 5 different mesh shapes, and then it has a test set that tests on a mesh of a completely different shape, so this U, which is not seen in the training set. And also the superposition test set tests on superpositions of electric charges. So more charges as the input than you would have in the training set, and it tests how well the electric potential is recovered from that. So now we can look at some results. So first, looking at the Darcy flow results, we were able to get with these, so BSMS is our hierarchical GNN, and here we have our transformal graph rewiring in this case. We're able to get pretty similar results to the UNet. It's, as I said, this is like not the data set that we're really looking to have great results on, but we can see that these state-of-the-art methods are pretty competitive with UNets. MGN is the just simple kind of vanilla message passing method directly on the mesh. And we can see that this is like really performing not on par with the other methods. And that's because we haven't introduced this way of dealing with the hierarchy. So even on a regular grid, dealing with hierarchical processing is beneficial. Our method, although it doesn't perform as well on this data set, and it's not really the kind of use case that we implemented it for, we can still see that it's improving largely on the just regular message passing, and that's pretty positive for us. So you can see a little bit more detail here when you compare here the just regular message passing and our method, that the prediction of on the Darcy flow is not able to get the information from this circle here to outside the circle. Whereas when we actually have the hierarchies, the hierarchical edges, then we're able to kind of start to get closer to the target. And that was our first result. That was a really positive signal. We then implemented it on the motor data set, and you can see here that we're really getting results that are closer to what we were looking to get. So again, the regular message passing is performing much worse than the 2 hierarchical message passing. So having these hierarchical edges is definitely beneficial. Although the perceiver is performing quite badly, and I'll go into a little bit more detail. Yes, what's the question?
Sorry, we have to give you a microphone.
Sorry, the question was just the unit was the best performer on the previous data set. Is there a reason you didn't try it on this data set?
Yeah, good question. So yes, so in these irregular meshes, you actually can't apply the CNN because it wouldn't be able to handle the like really high resolutions that you had from the picture I showed at the beginning. So yeah, that's why we didn't try. Oh yeah, it's error. So higher is worse, and lower is better. So yeah, the placebo performed quite badly, and I'll go into more detail as to why. And then like looking at our generalization test data sets, again, we see like a similar trend. The state-of-the-art hierarchical processing, hierarchical GNN method, BSMS, is performing either best or second best to ours. And in each case, our method is performing better than just regular message passing. But again, with the placebo having quite high errors. Our hypothesis for this was that due to this global rewiring, we're now able to like get messages across much larger distances, but it kind of loses the power that GNNs have to deal with local interactions. So in this case, we also implemented a model where we had message passing layers both before and after the placebo. And we can see that we're able to kind of recover the local interactions in the data and get much better results actually. So our error decreases quite a lot, especially on the irregular grid data sets. Whereas on Flow, where we have a regular grid, it seems to handle, placebo seems to handle it really well. So yes, those were our results. So I hope that from this you've learned that irregular meshes are present in a bunch of real-world applications, and they're very relevant to solving a range of problems. And our rewiring approach is competitive with state-of-the-art. We're not always getting as good as, for example, BSMS, but it's always performed in the irregular mesh data sets, it's definitely performing best or second best. It is a simple and efficient pre-processing step that you would just apply to your mesh before you train the model. And yeah, in that way it's pretty lightweight and easy to implement. And that hierarchical processing is definitely key to solving these PDEs on irregular meshes. So yeah, thank you for listening. Do you have any questions? Let's fire up another microphone. More questions. Okay, let's see if this one wakes up. Hello, hello. Should be working. Let's try another one. Tech problems today. Yes. Oh, is this one working? Okay. I think it was working. No? Was it? No, maybe it's like charge. That looks like out of charge. Sitting in a charger. But yeah, you can use this one. Sorry for the interruption. So many technical issues today. Thank you so much for this interesting talk, Lisa. Let's get some questions going from the audience, if there are any. And yeah.
Thank you. That was really interesting. My question is probably the following. Sometimes it's hard to solve PDE when in some local place you need to have really dense mesh compared to the other region. Like if you two source vectors close to one to another. Have you ever met such a situation, and can neural network tools help with this problem? And sometimes I see that mesh couldn't be converged and solver cannot proceed.
So, is this what? Yeah. Yeah. So your question is whether I've encountered situations where the mesh also is not able to.
Locally, it's very dense.
Yeah.
And sometimes you don't know how to construct this mesh.
Right. Right. So we actually get the mesh as part of the data. So constructing the mesh is not necessarily like the issue that we're trying to solve, and I haven't really encountered this before. But then I guess that would be an issue for our method, right? If we're not able to construct the mesh on these very high resolution areas. So, answer your question? Or?
Yes, that means I will follow your process.
Thank you for the great talk. My question is it possible to generalize, or did you try to generalize it to finer meshes? Because I guess now you kind of rely on a data set where you already know the exact solution. But then it would be interesting, of course, if you can extend it to a case where there's no solution, where the solution is really time consuming or so.
Right, so like you mean to test it, training on the same meshes, but actually testing on a much finer mesh for the same PDE?
Yeah, exactly, yeah.
Yeah, I mean, I think that's kind of what this generalization data set is supposed to kind of portray. I mean, we haven't tested the specific use case, but I think the idea is that like you would be able to generalize two different meshes. So whether that's more like higher density of nodes or even a different shape, but for the same PDE. So I think that's something we want to investigate more in the future, like really testing the generalization limits of these models, but that would be super interesting.
Two questions. Did you make a note about like computational efficiency? Because if you do this like smarter tree, like thing, it's like more efficient than a transformer that's just like connectivity. And second question, did you check for like physical invariances and did it generalize that? Like I know when you do like a unit on like fluid flow, if you have like a mass constraint or like an energy constraint, like energy has to be conserved. Usually it does really badly. Did you look at this in this example?
Right, so for your first question, we actually had results in our paper on computation time, which I don't have here. But so we did look at this, and actually the procedure was really fast. And I think that's probably, even though like it's fully connected, I think, yeah, actually I don't right now probably think of like a clear explanation why, but I think it's yeah, I mean maybe it's like more optimized a bit. Yeah, I mean I don't really have an explanation, but we do have results in the paper as to comparing the different methods. I think that also BSNS is doing this breadth first search, and it has to go through the different levels, so that's probably particularly slow. A tree approach, I guess that should be pretty fast. I don't have the results on top of my head, so I think if you look at the paper, you can probably see that. With regards to your second question, which was with constraints, like physical constraints, right? No, we haven't tested this, and that's a really interesting area to look into. I know that my colleague Vinny presented something very similar a while ago, and I think of the PDEs he was solving had some like unfeasible results. So I think that's like really interesting to go into as well, like seeing if it kind of matched up with physical constraints. And yeah, I think that would be really interesting. All right, any more questions from the audience? Otherwise, I have maybe, okay.
I mean, I just kind of two practical questions. How much data did you get? Because I'm assuming you got the data from the partner that you're working with. So how many samples did you get?
Yeah, that's a really good question that I would say I turned out off the top of my head. But I think for this motor data set, we didn't have that many samples. And yeah, I really didn't have it on the top of my head, but like I guess I got a few hundred. And then like the other two are publicly available data sets, and I think those just have quite a lot more. I think those goes around, yeah, probably nearer to 1,000. All right. I also have a question. I'll go before Brandon now because I'm the boss. So really interesting to see these comparisons with Perceiver. I was thinking of, do you think that Perceiver would do better if there were more training data? Because I guess like Perceiver doesn't have this like inductive bias towards a graph that the graph methods kind of naturally incorporate. Yeah, so I think definitely like that would do that. It would do better. Another point that we thought about, and that was like a time constraint, is that we actually didn't tune it as much as we could have. So I think that makes quite a lot of difference as well, especially with Perceiver. And actually, that reminds me of the answer to why Perceiver was quite fast, is that you have this latent, you do cross attention to get the input into this latent dimension, which is much lower than the input dimension that you might have. So maybe tuning the size of this latent vector would also improve the performance. But yeah, so I think like more data and a lot of hyperparameter tuning would definitely improve the results. Okay, cool. But you wanted it to lose maybe, so not necessarily. Sorry. This is just
I think I wound up asking pretty much the same question you last time. Maybe this will just be my running question. So for a lay person that has no technical understanding of this entire field, I'm curious if you could kind of paint a picture for what implications practice this research has and translate how we might see the knowledge that you derived here applied in real world situations that maybe I would understand.
Yeah, so I think this motor data set is a really good example of this. So yeah, we have this automotive manufacturer that they make electric motors, and they want to optimize for a specific motor design. So through our this prediction of the magnetic field of the motor that I was showing is like a small part of a bigger kind of whole motor design optimization pipeline. And so we get the kind of layout of the motor, we predict the magnetic field, and then it goes into this whole optimization further work. And yeah, so applications would be like motor design for a car manufacturer, and yeah, does that kind of answer your question?
Yes. Maybe just one or two more potential examples.
Yes, so you can also consider weather forecasting. So anything that's modeled by PDEs, so these partial differential equations, such as you can model the weather forecast through a PDE. If you can solve it, then if you can solve the PDE, then in your application you have some results. So GraphCast is a model that performs weather predictions. Using graph neural networks. It's not super related to our work in particular, but it uses GNNs and it's on PDEs. And then you can get very accurate weather predictions from this. Yeah, I think other engineering and manufacturing applications, it's in a similar way.
Thank you.
There is. Lots of questions today. I'm really happy about this.
Sorry. One last question. Seeing as the public data sets are much bigger than the one we use specifically, do you ever consider pre-training the networks on the public data set and just fine-tuning the data you have?
Yeah, that's a good question, and also an interesting research question that we have. So the thing is, those would be different PDEs. So for the moment, we're training on one PDE and predicting on the same PDE. We have different parameters, etc., but we still are using the same PDE. Generalizing to new PDEs, I think, is pretty challenging. But then we would get a lot more data. So I think that's actually something that we're looking to investigate and work on.
Thanks.
All right. Thank you very much for coming, everyone. Thank you so much again, Lisa, for this talk. I think it was really insightful, interesting. Feel free to hang around after. We still have some snacks and some drinks. We'll put up on some lounge music again. Maybe Lisa can choose this time. So we'll hang around for a little longer and mingle. And yeah, enjoy the rest of the evening. Also, thanks for the online crowd for tuning in. We had quite a lot of people this time, so that's great.
Thank you.
Thanks.